Okay, we have here today twin integrals. We've got the integral from 0 to 1 of ln t over 1 plus t squared dt. And then we have the same thing over here to the right from 1 to infinity. And now, of course, these are closely related. If I were to add these two together, what's going to happen is we get this other integral, just combining it into 1. And I've done this one before. This one's pretty easy. And this integral is just 0. You can get to this pretty quick with a u substitution. If you just do u equals 1 over t, what's going to happen is you end up with like the same integral but with a minus sign, which means it needs to be 0. So now for this problem today, I think what I'll do is I'm just going to focus on one of them. Let's do this one over here to the right. But by doing that and knowing that this one's 0, we can just quickly get to this other value just by subtracting this value from 0. So to get started with, let's just do a u substitution. I'm going to do my u equal for ln t, solve for a value of t. We're going to have t equal to e to the u. I'll take a derivative and we get dt is just going to be equal to e to the u du. Go ahead and substitute on it. Plug in infinity here and we're still going to infinity. Plug in 1, natural log of 1 is just 0. So then our numerator just becomes u. Then we're going to have 1 plus t squared. So this thing squared is just going to be e to u. And then dt is going to be e to the u du. And what I'm going to want to try to do is use power series on it. And you'll notice if I try to do it right now and like this is the input, this isn't going to converge because this is going to be going off to infinity. But to fix that, I can multiply by 1, just multiplying by e minus 2u, top and bottom. So when I do that, what's going to happen, now we're going to have u, this, multiplying this times this, we're going to have e minus u here. In the denominator, e minus 2u times e 2u, that's going to be a 1, just reordering it. And the second part's going to be e minus 2u. But now this is in good shape for our power series formula. I'm just going to kind of, like if we create a 1 right there, it's kind of similar to 1 over 1 minus x, which is going to be the same thing as the sum from 0 to infinity of just x to the n when absolute value of x is less than 1. So doing it with this, we just need to deal with this plus sign. The way I can write this is as 1 over 1 minus e minus 2u. That way the minuses cancel and give us that plus right there. This is going to be our input into the formula where we have an x here. So this is going to be the sum from 0 to infinity. And now it's going to be minus e minus 2u all to the n. And now for the convergence, we just need to plug this in. This is going to be absolute value e minus 2u. This here, the minus sign doesn't matter inside absolute value. This is going to be fine with these bounds because we're going off to infinity, so this is going to be going to 0. At 0, it's going to be 1, but we don't really care about the endpoints, so everything within these bounds is going to be less than 1. So we'll take this right here and plug it back in here in the integral, so it's going to happen, still going 0 to infinity. The numerator's unchanged, so we have u, e minus u. And then we need this sum, but I'm just going to rewrite it a little bit. So let's think of this right here as a minus 1, and with exponent properties I can break it up. So I can write this as minus 1 to the n. So I can write this as e minus 2nu du. Now let's take this and distribute it. We'll distribute everything in here. But now we have the same base here and here, so we can combine those together, and I can write this as e minus 2n plus 1u du. And then I want to swap the order of the integral and the sum. I can do it. We've got our absolute convergence right here. So let's just swap these. And minus 1 to the n is going to be just a constant with respect to u. So I can bring that out front of the integral, but still within the sum because it still has an n in it. But now with doing all that, what we have here, this is exactly, or almost exactly a Laplace transform. This here is a constant. So for now, let's just call this s, where s is going to be 2n plus 1. But doing it that way, what we have here is just going to be the Laplace transform of u. So for this Laplace transform, we have a formula for this, and I'll provide a link in the description if you want to check out more on the Laplace transform and where these formulas come from. But for this one, we'll use a different variable. If we have something like t to the n, the formula for this in terms of s is going to be s to the n plus 1 over gamma of n plus 1. So for this, the n value, the exponent on here is just going to be 1. So for the Laplace transform of u to the 1, it's going to be just s, 1 plus 1, that gives s squared, and then we're going to have gamma of 2 in the numerator. But for gamma of 2, we can relate that to the factorial. We have this formula for gamma of n plus 1. This is the same thing as n factorial. So gamma of 2 is the same thing as 1 factorial, or just 1 over s squared. So coming back and putting this back into our sum, let's rewrite this. We have our sum from n equals 0 to infinity. We still have this minus 1 to the n in front. Now instead of plugging back in our 1 over s squared here, remember s is going to be 2n plus 1. So let's put it back in terms of n, get everything as the sums in terms of n. So we'll have this as 1 over 2n plus 1 all squared. And let me just clean this up a little bit. And now with this thing here, I don't really have a good way to simplify it, but this thing is in the form for the Dirichlet beta function. So the form for that, let's just look at that really quick. So the definition is in exactly the same form as our solution. The only thing is, instead of this s here, we have a 2. So this here we can write as Dirichlet beta at 2. But the value for that, this is actually the same as Catalan's constant. And for this, I can give you an approximate value, something like 0.915967, something like that. And so maybe it's not so nice looking at the estimate, but we do have this nice expression, Dirichlet beta at 2, or Catalan's constant. And now coming back to what we had here, again, in the beginning, we said this whole thing needs to be equal to 0. Sometimes you'll see this constant written different ways as like a g or a c, but let's just, for now, we'll just leave it like this. And so just by solving this integral here and knowing that the whole thing put together needs to be 0, we can say that this integral here, this is actually going to be just minus Catalan's constant. So together, these equal just 0. So there you go. I thought this was a pretty interesting example. I think this came up because I was doing, not too long ago, I did this integral. And I think in the comments, someone actually brought up Catalan's constant, even though the solution for that one is different, but it was also a pretty nice formula. This one gives us something a little different. It was kind of nice bringing this pair into it where these two work together and give us the 0. So that's it for today. Thanks everyone for watching. Have a good day.